Hey everybody, this is Larry. This is me trying to do an extra problem that I haven't done yet. I've been doing it randomly, but I've been just going on the newer problems. I don't know. I don't know if that's been more views or no views. I don't know. But either way, just playing around with it. Today's problem is 3109, find the index of permutation. My disclaimer is that I jogged 14 miles today or something like that. If I'm a little bit slow, please be kind. Alright, let's take a look. Given an array perm of length n, which is a permutation of 1 to n, return the index of perm in a lexicographically sorted array of all permutations. Okay, I mean, I think this is something that everyone should know how to do for the most part, at least for competitive programming. Maybe not for, I don't know if you need to know how to do an interview, but the idea I think is very basic. I mean, not to say that, remember, I don't mean basic as in it's easy. It is simple, but it is, I believe, like fundamental to a lot of just, maybe not even part of the solution, but just like this idea of getting, like it's very basic combinatorics, I think, right? So yeah, so let's take a look. Yeah. That said, I don't remember it. So I mean, I have the ideas in my head, but we just have to figure it out. But yeah, yeah. Let's see. Okay, so you have 1, 2, so that's gonna return 1, right? All right. Or 0, I guess. Yeah. So the idea here is just to figure out the index of the thing that is left. There are a couple of ways you can do this. Because so what I mean by that is that you can think about this. Let's say there's a recursive construction, but not. I mean, we might not implement it with recursion, but we can think about this recursively anyway, right? So this, right? Then we think about, okay, well, 3 right now is the third most or the third ranked index, right? That means that this is less behind 1xx, whatever numbers is behind it, and 2, right? So that means that 3 is the third number in this case, obviously, and 1. This means that there is n minus 1 permutations over here, n minus 1 permutations behind it, or factorial. Sorry, I didn't. Yeah, right. And then now this is the 3. So then now we can say, okay, well, so the answer is going to be recursively just. We know what this 3 is going to be recursive 1 and 2 plus n minus 1 factorial plus n minus 1 factorial. And I didn't put a parenthesis here, so maybe that's just me lazy, for sure. Right? And that's like a very easy example walkthrough. It does get a little bit trickier with that because, for example, let's say we have a bigger thing like, I don't know, 3, 4, no, yeah, something like this, right? Then you still have the same idea. So you have 1 dot dot dot, and this is n factorial, 2 dot dot dot. We know that this is the third number, and of course you can simplify it now because we already did an example. So 3 is going to be equal to 2 times n minus 1 factorial. I guess in this case, 4. It's 3 factorial, but I won't. Okay, right? And then, but recursively, this means that okay, now it is going to be 2, 4, 1, and there are a couple of ways you can think about how to do this, right? With re-indexing to count the number of smaller numbers that is, you can re-index, meaning this is a 4, so let's re-index to a 3, right? Yeah, and then now you have a 2, and 2 again, it's going to be just 1 times 3 minus 1 factorial, and then now this is recursively. Maybe it doesn't have to be cursive anymore. You get the idea, right? And you read like this to a 2, for example. So so that's the idea. There are many ways to implement it. I actually, I'm not gonna lie. I think I'm the part that I'm a little bit ashamed of right now is that I don't remember, or not that I don't remember. I remember like I know like 5 ways of doing this, but I feel like those are not fundamental, and I feel like there is a more fundamental way of doing this, but I don't remember it. Because I know how to do this with segment tree, binary index tree, or Fenwick, what is it? Fenwick, and you can also do it with sorted list or something like this. So there are a lot of ways you can. So there are a lot of ways you can do this, but so that this is n log n and it'll be fast enough. But I feel like there is like a dumber way, but but I don't know. I don't know why I'm trying to. Yeah. I mean, I think there's a dumber way of doing it, but I just don't remember or don't know how off my head. Because and I'm a little bit ashamed because I feel like I've been just playing around with all these algorithms, and that's why. But okay, but maybe after we're done, we'll revisit to see what the fundamental way is. Like I feel like there is, but I don't know. But yeah, this is a mod problem, right? So the first thing we notice is that we're gonna have to do repeated n factorial stuff. So let's just calculate everything together, right? So that we don't have to, because if you do it lazily, obviously, this is going to take n times. You do the next one, it's going to n minus 1 times, n minus 2, and dot dot dot. If you do it with a silly loop, it's going to be n squared. So if you do it forward instead, then now it is going to be well, not n squared, it's just O of n, right? So factorial is equal to 1, right? And then for I in range of n, just let's start with 2, and maybe I need n inclusive. I don't think so actually, but we'll just put it in there anyway, right? And then we also put 1 for 0, so that's a little bit more accurate or easier indexing, if you will. Or this is an append is equal to I times fact minus 1. And the beauty of this is that because we have to do mod, otherwise it gets too big anyway, we can also mod this here. Yeah. Okay, and then now we just have to kind of do this thing and maintain this. I mean, another way that you can think about it is that for each number in the front, we have to get its rank, right? So there are a couple of ways to, that you can do this. Like I said, you can do this with binary index tree or Fenwick. You can also do it with seg tree. But the way that I'm going to do it is just with a sorted list, and this is just like you can also think about this as a ordered or binary search tree, right? Balanced binary search tree, and that should be fine too. Yeah. So then let me do it that way. Import sorted list, and the idea really is just, like I said, just to get the rank, right? So then now, for example, maybe we can do array is equal. I don't even have to do it. SL for sorted list, because I am bad at naming things, is just x for x in range of n. And maybe, yeah, from 1 to n plus 1, just to keep it consistent, maybe. Yeah, and that should be okay, right? And then now we have for x in perm, then we have current is equal to 0, is just, and what do we do here? Right, so then we have an x, we try to find its index in sorted list. So yeah, so that's just a very straightforward binary search thing. And this is the index. And what does the index tell us, right? The index is going to be the index of the element, but how many elements are smaller than it? Well, just the index, right? Because there's a zero-based index, so that means that we can do this. Okay, whatever, we'll keep the index. So index times factorial of well, the first number is going to be n minus 1. I guess I didn't really write it here, so whatever. Yeah, I mean, I guess will use SL as part of it, so that's fine. So SL is going to be n minus 1 factorial, right? And then we just add this, and then mod it, make sure we mod it. Well, we'll mod it again anyway. Yeah. And that's pretty much, one thing I did forget is that then now we remove x, so that now this will give us the actual rank in the future, right? I think that should be mostly it. Maybe I mess up some stuff, but which is way common and easy. Let's do, what would I have? Like 4 or 3, 2, 4, 1 or something like this. Okay, let's give it a YOLO submit. I mean, maybe I made some silly mistakes, but I think the algo is mostly right. Right? If it times out, then I have to do stuff again. But yeah, I mean, this is the general idea, like I said. So look pretty good. I think the elementary one may have been balanced binary search tree, but my mind jumped to sorted this already. And again, you can this idea you can do with any of these three. But yeah, because basically the idea would be to use the prefix sum, a dynamic prefix sum. Right? Let's take a look at. I just want to see if there's a. Okay, so Fenwick merge sort. Huh. Let's take a look. Maybe I did forget the merge sort solution. Oh, I get it. I remember this now, actually. Sorted this is easy. N square seems a little bit slow. Maybe they just kind of put it as a thing. In sorted is kind of dubious. Alright, well, yeah. Yeah, merge sort makes sense. Anyway, that's all I have for this one. Let me know. Oh, let me go over the complexity really quickly. This is going to be O of n for obvious reasons. This is an O of n loop, each of which does a log n query. So this is going to be O of n log n. Pretty straightforward, and this is also log n, by the way, but O of n log n anyway. Yeah. Like I said, the idea should be something that comes to you. I mean, you want to get to a point where the idea should come to you very quickly, because this comes up a lot. Like a lot of prompts may not ask you something like this directly, but they may ask you something that requires you knowing some of these ideas, and it is also the basis for a lot of, or maybe not a lot, but enough digit TP prompts, because you just have to figure out, how to add a lot of things without replacement in this case. But yeah, that's all I have for this one. Let me know what you think. Thanks for watching. Hit the like button, subscribe button, join me on Discord. Let me know what you think about this problem. I'll see y'all later and take care. Bye bye.